Morning. Laura, do you still have your Quaker link? I hope you bookmark your link from yesterday. Let's try to bookmark the link when I send it to you, so that way each time you log in, you should already be in Quaker link. Let me take a question for 2 minutes. Good morning. Let's try the question on the board. If you cannot hear me, please let me know. I try to make sure that sound is okay. If you cannot see the computer, cannot see the clicker question, or cannot hear me, let me know. So this is today's attendance question. We've been working with limit. Yesterday we started with one-sided limit, but I just assigned the homework this morning, so I think we may need a little bit more time with the homework, but this is one of the questions that we should practice for section 3 is how do you solve a question? How do you find the limit value analytically? Let's try this question. And you can see the numerator all have x, the denominator have x. That's why when x equals 0, the denominator equals 0. So since the numerator also have common factor x, we should factor out the x and cancel the x as a common factor. So let's work out the detail. Every time when I write solution on the board, I try to be a good model, but sometimes I just run out of space, which end up eventually get messy. But normally, we would try to figure out a way to present our answer to make it readable and organize the solution. I'll try to be a better example when I try to organize information, but try to learn a way to write down your solution step by step, so that next time when you see similar question, you can follow. If we don't do that, we end up. Ray, I don't see your link live. Are you having problem logging in? You can copy the link I posted. Are you not able to see the link? Because if you don't click on the link, your link is not alive. You can see Laura is online on the paper page, but your name is not online. Okay, click on that link. If you cannot click, you can copy. Like my cursor, when it's there, it shows the page. You can pretty much copy the address and open the separate tab and open that web page. You guys already have the answer? Let's see. That's right. Thank you. Thank you. Ray, do you have any difficulty accessing the website, web page?
Yes, sorry, I'm having some connection issues. Give me a minute.
Okay, you can open any browser and just type it in. It's my.flickr.com/6A653B784. You can just read what's on the screen, and that's the address of your page. You open a separate browser in the address bar, put in the website's address. So if you can't click on that link to make it alive, you may have to open a separate browser, like Chrome, IE, Firefox, any browser is fine. Let me try to, do you guys already have an answer? I can try to write out this. That's right, thank you. Do you have a? It's not, okay, that's right, thank you. Huh? Do you not see that? Yeah, okay. That's right, thank you. Okay, so the process is we should try to simplify this question to a question that's okay for evaluation. Right now, if we evaluate immediately, what we're gonna see is 0 divided by 0. So we would have to realize that 0 is causing the denominator to be 0, and very likely the numerator also have the x. So one of the way to handle this is have the x factored. The denominator is already factored. It's in the multiplication format. We write 5 times x. So for the denominator, 5 is a factor, x is another factor. Factors in mathematics, factor means things that multiply together. Those are factors of the denominator. Numerator, we have 3 terms. The summation or subtraction sign, separate terms. So essentially the numerator has 1, 2, 3 terms. All 3 terms have x. So x is what the 3 terms have a common factor. That is x. So whenever the term have a common factor, we can factor that out. This process is called factor of a polynomial. So we would bring the x outside this polynomial. And then that means we grab one of the x factor outside, put it right outside the parameter. Inside the parameter, you write anything other than that x factor. For example, the first one is x cubed. X cubed means x times x times x. You bring one x out, you have 2x left. So we have a x squared in the inside. So we do the same for the rest. The 12x squared, bring the x out, you have 12x left because one of the factor x is out. And the last term, if you get the x out, you have a -5. So this is how the numerator looks like after the factoring process. And then you can see the numerator have a factor x, the denominator have a factor x. This is being called a common factor between the numerator and the denominator. So whenever we have factor common, okay, I think your mic is on. Are you able to open the link? All right, anyway, I know you are attending, but the thing is you gotta figure out the answer, or you can type the answer in the chat. We cancel the common factor between the numerator and denominator, and we have this new limit calculation. And this allows us to have a lower power in the polynomial, which is intention, that would be reduce the level of difficulty. Numerator is x squared plus 12x minus 5. Common factor between numerator and denominator was canceled, so we have this. And then you can see right now in this new calculation of limit, we make x equal to 0. It's calculatable. So this time, if you calculate, make x equal to 0, and you can see that is 0, that's 0. So 0 plus 0 minus 5. The numerator basically is -5. So the whole calculation become is -5/5. And again, 5 will be a common factor. Cancel the 5, we have -1. So try to write this better. Should. All right, so the final answer for the entire limit calculation will be -1. I hope this is I try to be a better example, give a better example for how you would present your answer. So we have to have a habit that the answer that we write is for yourself to see and also for other people to see it. So when you, like 2 days later, you read your own notes, your own solution, and you don't understand yourself, then there is a problem with the way how you take your notes and how you write down your calculation. So make sure whatever you're writing makes sense, no matter who you show it to. So maybe you can also show your notes to your parents or your friends. If they can't understand anything that you're writing, then there's something wrong with the presentation. Presenting our idea is equally important than actually knowing the idea and knowing the solution. So we're all in a social world, and giving our idea or show our idea, prove our idea to other people is a necessary skill. So I hope that we kind of realize this is important. And also being able to write back a presentation actually helps us think better. So even for our own benefit, it's good to have like improve our presentation skill. I think that should be everybody. Anyone else? I think I had all the answer recorded. Ray, are you able to find the answer? Resend the link? Okay, yeah, let me do it again. So this time, try to bookmark it on your computer. And that way, next time when you are attending virtually, you will be able to go to it without have to spend a lot of time figure out your life. Okay, I guess you were re-enter the chat. That's why it's hard for you to. Okay, let's try again. Okay, I see. All right. Looks like your answer is being recorded. The answer should be -1. All right. That's today's attendance question. Do you have any homework questions you want to go over before we start today's class? Are you doing okay with the first 3 sections of homework?
Can you do number 3 and
1.2, number 3. Okay. And if I open the web page, this thing is in the way. You said 1.2, number 3.
Yes.
Okay, this question. We follow specifically how the definition is. Some of them are common terms in the definition. Before we finish this question, let me just write the definition, how we would phrase this. We're trying to prove this, okay, and then we're trying to follow that process in the writing. And okay, let's refer back to our notes from yesterday, how we write limit equal to something. This is our definition. First is for any epsilon larger than 0, we can find, or you can say there exists, or you can say there is. When you say there is, you're gonna have to find it. A positive number delta, whenever x and c, in this case, it's not c, it's 8. Whenever x and 8 is smaller than delta, we will be able to guarantee that x squared minus 9, which is on the left side of the equation, minus the 55, is less than epsilon. So we're saying epsilon is how we measure the distance between the intended limit, which is 55, and the function. Function x squared minus 9 minus 55 is the distance between the function and the limit value. We're saying this distance is small, smaller than epsilon, by making x is closer to 8. All right, so that's the definition. When you look at this, the first thing is let this be given. So when you see epsilon being any epsilon, epsilon can be given with any number. So I think the first one will be epsilon. Just try to fill out the link. This is supposed to be epsilon. And then there is a delta. This delta, we got to find it yourself. That one needs a little bit of calculation. Let's fill the rest. X minus C. X is approaching 8. So for this question, the x minus 8 is supposed to be there. And this is supposed to be the delta. And then fx minus the limit value is 55. I think that one should be f of x minus 55. This is the limit value. This is our f of x. And f of x is in our limit computation. That's the f of x. All right, it's less than epsilon. That's the intended, the process. So let me go back to the web work and see if what I was saying is right. So epsilon, and over here is the number 8, and then it's less than delta. And this is supposed to be epsilon, and here is supposed to be the 55. So all this entire process, all the things that we're entering is the same as stated in the definition of limit, except the last one, except the delta we have to find. When we see there is a delta, we gotta determine the true value of delta, which is going to be affected by the epsilon that we choose. So far, are we okay? Okay, then we're gonna work out the detail. If the epsilon is chosen, essentially we follow what we were doing before. You started with here because epsilon is given randomly, and then from here you're gonna slowly go back to here. Use this as the clue or the condition. Use this as our equation. We're gonna slowly solve x and then go back to x minus 8 and then add the epsilon value. So that's the basic idea. So we're gonna start with the x minus 9 minus 55. We're gonna start with this, right? And then that will be essentially x squared minus 9 minus 55 is minus 64, which is less than epsilon. That means it's less than epsilon and bigger than negative epsilon. Right, that's how you can remove the absolute value sign. And remember yesterday we were saying whenever you have a absolute value related question, it's often in the way. We have to figure out a way to handle the absolute value. For example, if A is less than epsilon, then a absolute value of A is less than epsilon, then A is less than epsilon, bigger than negative epsilon. That's how we read absolute value. Now, if you have bigger than, such as X or A, bigger than a absolute value, I'm not sure if this marker is using. If this is a larger than a number, such as epsilon, then X is larger than epsilon, or X is lower than negative epsilon. So this is two different kind of situation. When you are looking for a larger absolute value, it's either positive large or negative large. But if it's a smaller absolute value, you gotta be in the middle, right around 0. So that's what happened. Anyway, know how to remove the absolute value. It should be useful later for other things. And then we're gonna add 64 to both sides of the equation. Then you have x squared plus 64 in the middle. Plus 64 on the right, so we plus 64 on the right. We also plus 64 on the left, 64 minus epsilon. That will be what we have on that side. Okay, and then we'll have to have x by itself. So this time you're gonna take square root of x, and that's what happened here. So x is less than square root of epsilon minus plus 64, and bigger than 64 minus epsilon square rooted. Realize it's different than that. Okay, so then what do we do next? Like x and then x squared, right? Gotta take square roots. What do we do next? Remember, we're looking for the delta? So subtract 8, yes. So next thing we do, we do x minus 8. And then we have to minus 8 for all three. So this one is epsilon plus 64 minus 8. And this side would be root 64 minus epsilon minus 8. The next thing is we were supposed to take absolute value. So we would take absolute value of all of them. Okay, and then we don't know which one's bigger or smaller, but you're gonna try to look at this calculation and that calculation and take the smaller one. And then I realized that in the question it looks for a number multiply epsilon. How does it work? So we're gonna think of a number. I think this follow the textbook. We are looking for a multiplication. That's normally how I go about with this question. But the textbook went by a different approach. Sorry. Let me think of different way because we are looking for epsilon time. Like this is multiplication. We're looking for some number multiply epsilon. Right now the epsilon is inside here. It's not a simple multiplication. Even that one, the epsilon is incorporated into a root subtraction. So let's think multiplication. All right, so we're gonna go back to where we began. We have x squared minus 64, which is less than epsilon. And according to our textbook, we can factor this because x squared minus 8 squared. That's what's x squared minus 64. So you have square minus square, which would equal to x minus 8 times x plus 8. This is because the formula a squared minus b squared equal to a minus b plus a plus b times a plus b. So this formula, this calculation allows us to rewrite this. So we can write this as x minus 8 times x plus 8 less than epsilon. Okay, so maybe we can use this for a multiplication or division format. And from this, because you know this is less than epsilon, so immediately you can divide both sides by x plus 8 as the value. So you're going to have x minus 8 is less than epsilon over x plus 8. Right, this echo the intended target, which is looking for x minus 8 less than delta. So right now it looks like this is on the right of this, and this we have x minus 8, this will have x minus 8 absolute value. So this is more relatable to the intention, but there's a slight problem. This formula has x in the right, so we can have epsilon in how we represent delta. We cannot have x, so we have to find a way to relax this. So then we relax this so we can have a proper boundary for it. So then let's think about how do we relax this further. So this is a lesson. Our target will be epsilon time a number. So we wish to have x plus 8 to have a like this lesson. So it's in the denominator, it gotta be bigger than something. This is our intention. Right, so x is a number approaching 8. We can make x plus 8 bigger than right? We want this to be less than a number times epsilon. This got to be less than epsilon over this number. That means x plus 8 has to be bigger than a certain number. For now, we know x is a number that is close to, you see, x is approaching 8. So x is taking on a number really close to 8, such as 7 or 4. And the minimum thing is x cannot, it shouldn't be far away from 8. Okay. So natural boundary for this at least is absolute value, so it's bigger than 0, but should relax this better. Let's see when x is higher than 7. I mean, we see x is approaching 8, right? We can roughly assuming x is bigger than 7. If x is bigger than 7, this is bigger than 15. And this is less than epsilon over 15, or 1 over 15 times epsilon. Let me try that. I'm just trying to make up a factor, multiply epsilon, and answer this question. No. So there's 1, 2, 3. There's 6. There's 6. That means one of the answers wrong. It's we get partial credit for all the other ones. This one's still not right. Let me show you the solution given by Weber. I feel like I didn't relax the condition enough. All right, at the bottom part, you can see that what I was trying to do, it's a similar process, but the thing is we have to have, right, how 1 over 17. See, that's 1 over, I picked 1 over 15. So let's see the reasoning. Okay, since x is near 8, that's my reasoning. Here it says if x is near 8, we can simply assume x is between 7 and 9. That assumption, I was assuming x is bigger than 7, but that's putting an upper boundary and a lower boundary on x. This is very artificial. So this part is really to the personal preference for whoever writing up the proof. But it's my fault for not putting a lower boundary. So over here, we should, this is just a lower boundary. There should be an upper boundary, so x should be less than 7 and bigger than 9, since there's an absolute value. So if that's the case, we will have x plus bigger than 17, I think. So I feel like it's a bit bigger than 15. Right, so so if x is between 7 and 9, then x plus 8 is between 7 plus 8 and 9 plus 8. And x plus 8 is between 15 and 17. So the reciprocal is, if you take a reciprocal of this number, you're going to take a reciprocal of this number, and reciprocal of that number. So reciprocal all 3 sides. And now we have this inequality. So then the 1 over 17 is a lower bound, and 1 over 15 actually is the upper bound. That's my mistake. I was using the 1 over 15. But essentially, this is the fundamental reasoning. And what we wanted to do there is to see, we got x plus 8. You cannot use x plus 8 in the denominator as our boundary, as the boundary for delta. That's why we try to figure out a way to remove the x from the whole formula. That's why, but when I try to relax the condition, I know x is approaching 8, but the way I relax this is not sufficient. The proper way to do it is put on boundary on x on both ends of the x value. I only put the lower boundary on the x. There should be a lower boundary and the upper boundary. Using those boundaries, we can determine the value of x plus 8. Now, if x is between 7 and 9, and then x plus 8 is between 15 and 17, and therefore 1 over x plus 8 is between 1 over 15 and 1 over 17. The 1 over 17 is actually the lower bound, and here we really are looking for the lower bound, so it should be the 17. And that's it's a mistake on my part. This should be 1/17. We should try one more example if you want to, because I made a mistake there. Does that answer your question? Do you want to try your version of it?
Question 6 was the same thing.
Question
6 on the.
6,
yeah.
okay. I guess we can have one more try on the same setting. Question, this one. Okay, so let's follow through. The process will be, this is epsilon, and this is x minus 8. It's less than delta, and f of x is 8 minus x, and the target limit value is 0 in this case. Okay, and it's supposed to be less than epsilon. Epsilon delta definition of limit value. All right, so this is just like you said, is almost the same question. So let's run through the whole process. I feel like for many of the limit calculation or limit proof, there are multiple ways to prove it. Math is like that. If it's a calculation question, there's only one correct answer. But if you're talking about proofs, there could be several different ways to prove something that's right. And then logically, that's true. You can prove by saying if this is wrong, there's a confliction. You can prove something by simplifying it to an easier question, or you can prove this is coming down from a harder question. You can prove a harder question saying this is like a different version of that harder question. So basically, there could be a lot of different ways to solve something. And I feel like my way is more to the true value of the mathematical formula, but the book chooses a different approach, and this is actually follow the book. And all right, frankly, this thing, the choice of delta can be a couple of different settings, but this is really because epsilon is already there. We're looking for a number multiplying, so we kind of have to follow that multiplication way of thinking. Okay. Going back to the question, we intended to have fx minus 0 less than epsilon. So our f of x is at 8 minus x. And minus 0 is, you don't have to write minus 0 because it doesn't change the value. And that is less than epsilon. We're going to use this to start the calculation. Oh, that one, see over here, we were looking for the delta. Then x minus 8 supposed to be less than delta. Right here is less than delta, but here you have 8 minus x less than epsilon, which essentially means that x minus 8 is less than epsilon. This one has no square, so we don't have that factor process. So you can see that x minus 8 is less than epsilon, and here you have x minus 8 is less than delta. So that answer is simply 1, because that is the same. We have identical term on the left. That's why we gotta have the identical term on the right. So this answer will just be 1. That's this one. So this is question number 5. Number 5 actually is slightly easier than number 3. That's this one. It's easier because it's degree 1. The x is degree 1. For that question that we had, it was a square, which is why we use the formula a squared minus b squared to factor it. Any question? Are we okay? Do you need to repeat that the other question?
Can I see the work again?
Okay. That's the audio on this one. F of x is 8 minus x. So this is basically 8 minus x minus 0 less than epsilon. But then this is x minus 8 less than delta. So here you have x minus 8 less than delta. Here you have 8 minus x less than epsilon. Within the absolute value, like a minus 3 has absolute value 5, but 3 minus 8 has absolute value 5 as well. So these two are the same. The difference between 8 minus x and x minus 8, they're opposite. One negative, one positive. But when you put on absolute value, they're the same thing. So a minus x, x minus 8, they have the same absolute value. So that was the answer for this question is just 1. Any other question? You okay? Any other homework question? Okay, so yesterday we mentioned the one-sided limit, and this morning I set up the assignment. We may be able to try a few questions before we move on to section 5. Start with the first question. All right, this question asks for us to determine the limit for, let's start with the first two questions. The graph is the graph of a function. So in this question, we're looking for, the first question is for the limit of the function when x is approaching 2 from the left. Negative means left, positive means right. So this is approaching 2. Here, that is 2. This is a 2. This is a 2. So if you're approaching 2 from the left, which is the negative side, it's going here. So you can see that value is 2. That limit, we okay? We okay? All right, next one is limit of g of x when x is approaching. Right, x is approaching 2 from the right side. That's the right-hand limit. Right-hand limit, you find 2, and then we're approaching 2 from the right side. It's the positive side, so it's approaching this way. You can see the limit is, it's -1, it's -2. So this limit is -2. Any question? Right, so that's the one-hand limit, one-sided limit. So you have, this is 2, and this is -2, and then we can answer for the one has no sign. X approaching 2, we're saying what is this limit? Now, left-hand limit equal to 2, right-hand limit is -2, therefore this one, it does not exist. Okay, so we will write B and E, B and E. Question number 4 is try to find the limit when x is approaching 0, and then we go back to the question. Okay, at 0, on the left side is going to 1, 2, 3, 4. That's 4, right? On the left side is going to 4. On the right side, what is it? It's -2, right? So they're not equal. Therefore, the limit is, it does not exist. So we will answer D and E for the limit at 0. And the number 5 is asking for the function value at 2. So we go there and then to there, the solid point. That's the function value, okay, which is actually 1. There's empty there, it's empty there. When you have an empty point, we may have a limit, but we don't have a value, we don't have a function value. So the actual value is 1 for the last question. And this is pretty much how we read the graph in order to determine the limit. And that's our first question. Any question? We okay? All right. Maybe we can look at a computation example. Let's see this one. Okay, the question says we want to find the function of this limit when x is approaching 7 from the left. So here is our formula, and we realize if we make x equal to 7, then the numerator would be 7 squared minus 7 squared, which is 0, the denominator. Denominator will be 7 squared minus 6 times 7 minus 7, which is also 0. So this is a 0 divided by 0. Normally, we will think about, you can think about value to solve it. For example, if I try to solve this question with numbers, I can try, see x is approaching 7 from the negative side, means on the number line, the x is on the left of 7, so it's less than 7. We can choose x value that is smaller than 7, so the numerator would be, I'm using numbers. Let's try to enlarge this. So let's try to make x equal to 6.99. So 6.99 is pretty much almost 7. So 6.99 minus 7 times 6.99. So that's kind of how you find the one-sided limit using number. And the denominator will also be 6.99 squared and minus 6 times 6.99 and then minus 7. So I'm using this as my calculator, but you can see the number is roughly, well, can't see where it's approaching to negative 8.874,844. So I'm just trying to use the number. It looks like I'm not close enough. So I'm adding 29 to it, just so we're using 6.99999. I guess that should be close enough. This is try to solve a limit calculation with numbers when not getting there. So that looks close enough. So the computer thinks that you have a accurate enough answer to the correct answer. Of course, this is a numerical way try to determine the limit value. And then you can see numerical calculation sometimes give you the exact, well, close enough answer. Sometimes it may be a little bit off. Most of the time it's a little bit off. It's just that the computer is forgiving, even though it didn't answer the correct answer, then the computer feel like that's close enough. All right, so this is how to handle the limit calculation numerically, and then we can do it analytically. Because we're gonna polynomial, we have x, when x equal to 7, we know it's 0 divided by 0. So x minus 7 is a factor in the denominator and in the numerator. So analytical approach is to have a better understanding of the function and actually factor out any common factor. So after factor out the common factor, we should have a slightly less complicated limit to work with. So for example, in the numerator, if I factor out x minus 7, what's this? It will be x minus 7 times
X plus
10. No. See, there's x, right? That has x, that has x. So x is a common factor, right? When everybody has x, x is a common factor. Yes. So you can get x outside, and without the x, it would be x minus 7. Are you okay? All right, and the denominator. Denominator, if you factor out x minus 7, what do we have? It's x plus 1. Okay. And then we're going to continue. We factor out the x minus 7, and you see x minus 7, you observe x minus 7 from the numerator and the denominator, and we can have an x in here and have x plus 1 in here. Now, if you make x equal to 7, you have 7/8. And that's the true value of this calculation. So instead of putting a decimal number, we should be putting in 7/8. Answer to the question, like 0.875. That's the actual value of the limit. What we have earlier is a very close value, but it's not the true value yet. All right. For the factoring, there are other ways. I did mention synthetic division. If you have a hard time trying to factor this out, you can also do synthetic division, which will look like this. The numerator, the coefficient is 1, -7, and 0. And then what we're gonna do, we're trying to 7. So we do 7, drop down to 1, and then there's a 7, there's a 0. There's already a 0 there. So altogether, this is x. So this is x minus 7. It's multiplied by x over here. There's a 0, so we don't have to write the 0. On the other one, you have 1, -6, -7, the denominator, factor in the denominator. And we still put in the 7 in here. You drop down the 1 time, and then you have a 7 plus, and you have a 1, and then 7 times 1, that's 7, and there's 0. So this will give us x plus 1 in the last row. The last row is 1 and 1, so that's x plus 1, which means that x minus 7 is multiplied by x minus 1. So this is again using synthetic division as approach to handle the factoring. Any question? So I'm just saying, you can have several different ways to handle the factoring. Figure out one that actually works all the time. So sometimes you have one method, sometimes another method, where we each have their own preference. So whichever works should become your routine. That way we have that confidence that if I see this kind of question, I'll do this, and then everything will work out. Any question? All right, so that's the first 4 sections. Today, we're gonna start section 5. We are in sequence. Okay, section 5. Assuming we understand some, we have all the limit concepts. All right, let's talk about continuity. Then maybe we can do a little bit more limit. I feel like there are something I should talk about limit. So the whole chapter 1 focuses on limit and continuity. So 1.5 is talking about continuity. When we say continuity, we mean continuity of a function. So when it's not continuity of time, it's not continuity of other stuff. Continuity of a abstract function. All right, suppose you have a function that's already defined on the interval. I mean, to be continuous, you have to have a path, have a continuous playground. If it's isolated, then there's there's nothing to talk about as far as continuity. For example, there are a lot of things in life that are discrete. There are a lot of other things that are continuous in life. For example, when we talk about mistakes, when you see how many mistakes you're making when you're writing a paper, the number of mistake is discrete. You can have 1 mistake or 2 mistakes. And normally we rarely say we made half a mistake. So as far as number of mistake, we don't have integer number. Therefore, number of mistake is by nature, it's a discrete function. It's not gonna be continuous at all. So, but there are a lot of things that are continuous. Most of the algebraic functions that we define are continuous. Let's try to follow this definition. Suppose you have a function that's defined on the interval, and if the function is continuous at a number c, if the limit of the function equal to f of c. Basically, we're saying the first and number 1 statement saying, if you are looking for continuity at a single point being the number c, at point c, you have to guarantee that limit of these function at this point c can be solved using substitution. So most of the situation that we had earlier in the limit calculation, most of those functions are continuous whenever you can solve it by, let's plug in the number, let's substitute the number, and things will work out. That's continuous function. Now, if you plug in the x value, the c, if you plug in number c, it didn't work out, okay? And the reason for all those limit calculations running into an issue when you calculate using substitution, all because the function that we're calculating for limit 4 are not continuous. So whenever the function is not continuous, we see this function have a discontinuity at the point c. So this is the first statement is talking about continuity at a single point. Second statement saying the function f is continuous on the entire interval. An interval is at all the number within the left boundary and right boundary. An interval have infinite many points. So there's a big difference between the first statement 1, statement 2. Statement 1 is talking about continuity for a single point. Statement 2 saying f of x is continuous on the entire interval if f is continuous at c for all the values c and I, meaning that the function has to be continuous at every single point in that interval, right? And a little bit generalized to when you see the function is continuous everywhere, that's when the function is continuous on the interval negative infinity to positive infinity. So the entire number line is a big artificial interval, and the endpoint for the whole number line is from negative infinity to positive infinity. The interval negative infinity to positive infinity is also considered an open interval. If we remember, if the endpoint is not achievable, it's called open interval. If the endpoint is possible to achieve, it's closed interval. So closed interval is when the endpoint is included. Open interval is when the endpoint is not included. And obviously being infinity, having a negative infinity and positive infinity are artificial limit, artificial boundary. So these are not achievable. That's why negative infinity to positive infinity is an open interval as well. So here we see open interval. Here we mean any open interval. And that's the definition for continuity. Any questions? So essentially we define continuity based on limit computation. That's why we often talk about continuity after we have some understanding of limit, because we've done so many limit calculation. For some of the limit calculation, you can simply plug in the number that x is approaching to, and that will be your limit. Whenever you can plug in the number and calculate it, and that's done. And that's because the function is continuous. Whenever you plug in the number, you got 0 divided by 0, you got undefined. Whenever there's any issue at all when you plug in the number and you can't get an answer from it, that's because the function is discontinuous. So for discontinuous function, we either have to try a different approach or we will just answer the limit does not exist. Any question? Right, so limit calculation is closely related to continuity. Again, we're going to look at graphs. A graph of a function often provide a more intuitive way about limit or about continuity. Now let's look at this function. This function is being defined kind of like a 3 piece. So you can think of it as piecewise defined function on the graph. And give the interval on which the function is continuous. Okay, basically when you think about continuity, it's like try to move along the function graph. If you can move from the left to right and it's continuous on the entire interval, if you are stopped, if there's any empty spot, any breaks, then it's not continuous. For example, let's start from x equals 0, and then we move along the graph. You move all the way back here until you reach 1. There's an empty spot, and then we're stuck there because there's no function value at 0. We got a discontinuity at 0. But before we reach the 1, it was fine, right? Right. Whenever you can go through, you got a continuous function because you have left limit, right limit, left limit, right limit. Whenever any value you pick from 0 to 1, any value in the middle of 0 to 1, you can always go by left and right, they all arrive at the same thing. So we do have limit for all those points between 0 and 1 until we reach 1. At 1, we would have a left limit, we would have a right limit. However, there's no function value. Any question? To have a continuity, we have to have left limit, we have to have right limit, we have to have the function value, and the function value has to equal to this limit. Okay, so as far as answering this question, we're going to answer with intervals. Let's give interval for the function where the function is continuous. All right, so we're going to try to specifically understand what do we mean by interval. Right, interval. Interval is part of the number line. Specifically, whenever we talk about interval, unless we noted otherwise, it's interval of the x value. So when we talk about interval, we're going to look down at our x-axis. So it looks like this function is defined from 0 to 3. Okay, so whenever we talk about interval, we want to provide the intervals like this: A, B. This will be a closed interval, right? A, B. This will be an open interval, and A, B. This is a half closed, half open. A, B. This is a half open, half closed. Anyway, so A and B is supposed to be the endpoint of the interval. I'm providing example hypothetically, a hypothetical interval. Now, in our example, what we see here is from 0 to 1 is continuous. We have to stop at 1. So this solution for this question, interval for which it is continuous. Continuous interval is from 0 is included, till 1. I have to write open interval at 1 because you see at 1 there's no function value. So the graph, or whatever you're traveling, you're getting approaching 1, but you're not gonna get there. This is a no, there's no function value. We okay there? So at 1, we're gonna stop, and then we're gonna start pick up. Suppose we go from the right side, and you can start from 3, you travel left, and you're gonna have to stop at 1, right? But before the entire piece of the function graph from 1 and then 2 and then 3, this part is connected or continuous. Are we okay? So we're traveling from left to right with no issue. That is a continuous interval. So we can see from 1 to 2 to 3 is all continuous. With interval, we only provide the left endpoint and the right endpoint. Left endpoint is 1, right endpoint is 3. That's our second interval of continuity. So this function is continuous from 0 to 1, and then from 1 to 3. It has one discontinuity at 1. So this is how we represent discontinuity. We're saying at 1, there's a break. Any question? We okay? All right, this kind of function, because the left side and the right side seem to be arriving at the same thing, this is the kind of function that's fixable, because all you have to do is fill in that spot. If we have this one more a condition saying f of 1 equal to 1, fill in that block, and then the whole thing will be continuous. So this kind of discontinuity have a special name. If it seems to be fixable, and then we can see it, we call that removable. Removable discontinuity. Among all the discontinuity, I guess this is the one that we like the best because we can fix it and make it continuous. There are discontinuity that we cannot do nothing about it. So if it's this way and that way, like we see on the web work, approaching 2 on one side and approaching -2 on the other side, then there's nothing you can do. You can't really connect them immediately because it's going to be a vertical line. A vertical line are not considered a function, so we can't really fix it. So this is a kind of function that we could easily fix it by adding that one single spot. And this kind of is one special type of discontinuity. That's why people gave it a special name to it. The answer to the question will be those two intervals. It's our first example. Any question? All right. As you can see, the study for continuity, it ended up being kind of also the study of discontinuity. So if you want to know where is this function continuous, it's kind of like asking where this function is not continuous, because all you have to do is take out the not continuous point, and what you have left is the continuous interval. So we kind of discontinuity and continuity seem to be opposite, and therefore you got to know your enemy, you know. So if you want to know when it's not rain, all you have to do is find out when it's raining. Okay, so this is our second example. Here we have a special, and you might hear this again. It's called a floor function. The floor function, we have an interesting notation. I can't even find that on the keyboard. It looks like vertical line, and then you have a small chart, a small like L. So that's the notation for the floor function. So f of x is defined as x floor. What does it mean by floor function? It returns the largest integer smaller than the input. So the floor of 3.1 is 3. Like the floor of pi is 3 because pi is 3.14. And when you try to find the floor of a value, you get rid of any decimal, only keep the integer part of it. That's pretty much what do we mean by a floor function. Any question? So that means whenever you have a number, it returns only an integer value. So you can see if it's a number between 0 and 1, then the floor would be 0. If it's a number between 1 and 2, then the floor would just be 1. If it's a number between 2 and 3, which is the x value, and then what's the floor would be 2. So on the graph, you can see the graph of the floor function is what people call the step function, because it looks like the steps, right? There's no connection. There's There's nothing in between of these, and this is a kind of function that has infinite many discontinuity. It's discontinuous at 0, at 1, at 2, because whenever you reach a new integer, you're gonna go jump up, and there's nothing in between. So at 2, the floor of 2 is 2, and then at 2.1, the floor of 2.1 is 2, and then floor of 2.3 is 2, and so on. The floor of 1.5 is 1. So anything in between 1 and 2, the floor is all equal to 1. So what you can see if you look at from the y value standpoint, the only y value that we have is there 0, 1, 2, 3. There's nothing in between. There's no 2.5 for the y value. There's no 1.5. The y value only takes on the integer. The x value is any number, all real number. That's the step function. Any question? Okay. This one we're trying to find the interval of continuity. We will be having a hard time since there will be infinite many solutions. So if you want to write out the solution, you may have to figure out a way to represent it. And we can represent it with some omission, or we can write the solution with a formula. So for example, I can see this is from 0 to 1. I can see the 1 is included. So in the middle, we have 0 to 1. Right, and then you can see this is from 1 to 2. So the 1 is solid. 1 is solid, so the 1 to 2. And then from here, this part is the interval. See, whenever the question asks for interval of continuity, you're not looking for the y value. I mean, we know the y value is integer 0, 1, 2, 3. We're not looking for y value. We're looking for interval continuity on the x-axis. So this interval is interval of x values. So here's 2 to 3. So you can see all these have similar format. The beginning point is included, the ending is not included. And you can see this process has to go on and on. Floor function really have infinite many pieces over here. Is 0, not included, and then -1. Okay, so this is the first way to write the answer. You have to write dot, 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 both left and right to indicate this interval. There's really infinite many of them. This is one way to represent it. Another way to represent it is to write a formula. You gotta write all the intervals. You write union notation, or that is saying or 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4, or 4 to 5. It's going to be infinite many interval because there are infinite many of them. You can write this way. We can write n to n plus 1. N being integer. Okay, so this is indicating what kind of n do we want it in that notation. So this is a formula representing we are union of all such intervals where the n is supposed to be the integer, such as 0, 1, 2, -1, -2. So n is any integer belong to this set of intervals. So this way is avoiding having to write all those dot, dot, dots. This is using that notation to indicate all such interval are being in this whole union of intervals. Any question? So when we talk about continuity or representing interval continuity for any graphs, we have to have some understanding on how do we represent interval and how do we determine the endpoint of the interval. Sometimes we have to watch out for open interval or closed interval notation. These are the interval notation. That example. Okay, so let's look at a special situation. You often hear the word that this function is continuous on the closed interval. This is very important because on the closed interval, if the function is continuous, we have a lot of special property. If the function is continuous on closed interval, it is guaranteed to have maximum value and minimum value, which mathematically is very important. That's why we need to know if a function is continuous on closed interval. All right, so number one, we have already defined when we see f(x) is continuous on the open interval. right? If it's closest on the open interval, because the interval is open, so any number on the interval, like number C, you can find how to go to that C from the left and from the right, because C is not the endpoint. Endpoint is not included. Therefore, C has to be a middle point. Because it's a middle point, it would have left part, it would have the right part. Therefore, the limit of the function at C would have left limit and right limit. It will be a two-sided limit for any number in between A and B. So this is why we can easily define continuity on the open interval, because any number in that interval will have two-sided limit. Now, we have a little bit problem for the endpoint. If you want to prove the limit is continuous on a closed interval, now A will be the left endpoint. At A, you will not be able to have left limit because A is on the left corner. Yes, the graph will show what is going on. So to be close on the to be continuous on the closed interval, we have to watch out for the endpoint. So let's try to look at graphically how it looks like. You got a number line, and then on the number line, you have this number A and this number B. And we're saying the function has to be, see that, and the function has to be continuous on any number between C, so that's a C. We're saying whenever you get a number in the middle of A and B, that's a point on the open interval. We're saying the function is continuous on C. So at C, you will have a limit, limit on the left, limit on the right, and function value in the middle. All three are equal. Okay, left limit, right limit, middle point, the point, they're all equal to the same thing. That's continuity at C. And that's the definition for continuous on the open interval. Now, on the endpoint, when at A, you see, when you try to get to A is the left endpoint of the continuous graph. Therefore, at A, you will not be able to go to A, approach A from the left, because it's not defined or it's not included in this discussion. So we will have a function value at A, and we will have a right limit at A. We will not have left limit. Therefore, we don't have the double limit situation. So the continuity failed or it cannot even be defined. And that's why for continuity at the endpoint, we'll have the issue for this. Because that two-side limit, x approaching C equal to f of x, this limit can't happen. And therefore, we still want to guarantee the continuity at that point. What do? We will talk about only the right limit. So we're saying the right limit of the function equal to the function value at A. And then at B is the right endpoint. Therefore, you can only approach B from the left side. So on B, you will have a left limit. So at right endpoint, you have a left limit. And on the left limit, which is A, left endpoint, you will have a right limit, which equal to the function value. So f of x at A have a right limit that equal to f of A. F of x at B will have a left limit that equal to f of B. So I hope I'm making sense of all three conditions when we talk about continuity. Any question? Right, so we have to specifically talk about A and B because A and B do not have a limit. They only have one-sided limit. They don't have the two-sided limit. So A and B have to be taken out and specifically talk about the condition as far as the continuity. This is like you can call that one-sided continuity because it's continuous on the, so on the A, it's continuous on the right, but not on the left. At A, it's continuous on the left, but not on the right. Maybe not on the right, but we're just talking about this particular interval there. So this is the definition for continuity on a closed interval. You figure out where's the computer cursor. All right, so that is our definition for a continuous function on a closed interval, which is over here. Okay. Before we run out of time, let's talk about a couple of property. Continuous function sounds like a really high requirement. Everything got to be all continuous. But actually, there are a lot of algebraic functions that are continuous. Essentially, we have a lot of functions that are continuous. We also have a lot of functions that's not continuous. We're going to try to focus on the continuous function. When we see discontinuous function, we're probably going to single them out and talk about them right then. So right now, suppose you already have two continuous functions, such as f of x equal to 1, constant function is continuous. F of x equal to x, the identity function is continuous. F of x equal to x plus 9, f of x equal to x squared. So there's basically a lot of example of continuous function. Suppose you get two continuous functions. The first one saying adding up two continuous function, the result is also continuous function. Subtract two continuous function, that's also continuous function. Essentially, since summation or differences create new continuous function, it doesn't really change the continuity. C is if you multiply, number two, if you multiply a number C to your function, and that's still continuous. Number three, if you multiply two continuous function, that's still continuous. So you see, we're basically doing an algebra on functions and talk about the continuity. The same thing will happen for other things when we talk about derivative. You have two functions that has derivative. What about the derivative of the summation? What about the derivative? So we are talking about all these algebraic maneuver whenever we have a new topic. So you kind of have to get used to this. We talk about limit, right? When you have a limit of two functions, let's talk about limit of summation and so on. All right. Division, if you have two continuous functions, division will still be continuous except when g is not 0. So basically, g equal to 0 would be a discontinuity. So number 4 have little condition on top of it. So it's possible that a division is not continuous entirely. It will have some special discontinuity. Number 5, power of continuous function is still going to be continuous. Number 6, root of continuous function is still going to be continuous if n is odd. If n is even, then we do require function to be positive. So the interval for the function to be continuous has to be the interval of the function is bigger than 0. So that's a special thing. This one, so division and root are two common example when we have specific discontinuity. And last one, composition. So essentially, composition continuous function should still be continuous except when one function falls into discontinuity of the other function. So that's something we might want to look at when we see it. So what can be a little bit complicated is all the one that has occurrences. And those are the one that possible cause some discontinuity or complicate cases. The rest of the example, these are talking about what are the interval continuity. And we've had a couple examples. When you have graph, it's quite easy to say continuity. When you understand the function, such as the sine function, sine and cosine are continuous. They're wave, it's periodic wave. They have no discontinuity. This is continuous for all real for the entire interval. So we do have some common understanding before we're able to talk about the continuity or interval continuity for all these functions. So this example is similar to this example. I'm going to try to do it tomorrow, but today we'll just try to introduce the idea of continuity and we try to work out more questions tomorrow. And that'll be it for today. I hope it's okay. Hopefully it's not too fast. Really bring out any question that causes a problem or confusion. We're trying to catch enough time so that later when we have harder section, we can spend more time. So at the beginning, supposedly, if you are all feeling fine, and I'm feeling fine moving forward to the next section. So bring up your question if you feel like this is too fast. Or we got more example, we're gonna do more examples. We'll pause. I'll see you tomorrow. Thank you. Today's Thursday already? Okay, that was fast. Yes, Tuesday. See you Tuesday. So that's class tomorrow. Yes, I will be posting the 1.5 homework tonight. Thank you. Yes, I think Monday is MLK holiday. The 20th is a holiday. Yeah. Tuesday will be the next.
We still haven't heard back from the registrar. So we were wanting to know what we should do about completing the homework since we can't access it.
Right,
very easily.
let me log out, then we can